I asked for a brief introduction class because I need every minute I can get, because when you're in a VBS and folks start coming in, you have to stop. This is a problem. It's an honor to be here tonight. I have lots of things I'd like to just say by way of introduction, but I don't have time. So thank you. Are you ready for a lesson? Yes. I hope so. And I have a policy when I teach science. You are joining my science class tonight. This is Biochemistry 101. And my policy is I don't allow sleeping. And if I were in your seat, having had a nice big supper, I would be very sleepy. But I don't allow it. So please try to stay with me. I hope what I have to say tonight will stupefy you. That's my goal. When we finish tonight, I want you to walk out of here more in awe of the God we serve than you've ever been. That's what it's about. This lesson and next Wednesday, we're going to examine evidences for the existence of God found in the natural world using the methods of science. Most of the information I'm going to share with you tonight has been only discovered by humans in the last 75 years. You have lived, class, in one of the most exciting times in the history of mankind with regard to science, because we have learned more in the last 75 years about life at the biochemical level than in all the history of mankind prior to this. So my job is to summarize that in 35, 40 minutes. God has opened the floodgates of information about himself in the natural world that we never knew 100 years ago. So tonight, we're going to focus on the evidence. What happened here? That is not my first slide. There we go. I guess we were on something else, weren't we? Okay. That's not the slide. What happened? Got to fix this in a hurry. There you go. I just needed to go one further. We got a slide stuck in there that doesn't belong. So go ahead and get me there. There we go. We're going to go to the evidence of the chemistry of living things tonight, class. And as we do so, I want to help you see things. And please understand, I'm not expecting you to remember or be able to teach everything I'm going to tell you tonight. But I hope you get the major point, and I think you will. April 8, 1966. Some of you were alive then. Raise your hand and make me feel better. This came out in Time magazine. Is God dead? Well, I will tell you, with the increase of knowledge starting in the 1950s, and I was going through junior high, high school, and college in those days, and I can tell you from my personal experiences that in the sciences we were uncovering things in such a rapid pace that men truly believed, I think, that we were going to uncover the secrets of life. And the further we went down that road, the less we need God. And so the sciences were moving away from God. And at the same time, many religious groups were going right along with them. So this article by Time magazine in 1966 was very much in tune with the times. There was a song written about the same time. We just sang it. Our God, He is alive. A.W. Dicus, many of you know he was the academic dean at Florida College. And it is the case that I literally sat in his desk because I was dean there for 13 years myself. 18 years, as a matter of fact. And then later the president. But he was also a physicist and well-respected, had a number of patents to his credit. Anybody know one of his patents? By the way, this is a class and you're allowed to talk when I ask you a question. Anybody know a patent that A.W. Dicus had? You use it every day in your car. The turn signal, that automatically clicks off. He invented that. Anyway, A.W. Dicus did not at all agree with this, and I'm so glad you sang it enthusiastically. Our God, He is alive. In Him we live and we survive. And I hope you meant it in every word that you sang. The third verse was what I asked him to lead second, because I wanted you to sing that too. It says, secure is life from mortal mind. God holds the germ within His hand. Though men may search, they cannot find, for God alone does understand. Our biology professor at Florida College in the 1960s, whose name I will not give you, refused to sing that verse. You know why? Because he literally believed the time was coming in the relatively near future when we would know the secrets of life, unlike that verse says, and that mankind would have discovered how to make life. I wish that professor were still alive today, because class, what we have learned in the last 75 years has put the notion that we can somehow figure out how life works to bed. We are farther from understanding how life came about without God than ever in the history of mankind. The evidence is overwhelming that somebody amazingly powerful made this, not the other way around. But it is the case that a number of scientists in those days, including one of our professors, and we were all Christians, wouldn't sing verse 3. Here are a couple of the things said in this magazine. Hamilton and Altizer are theologians, class, preachers. And they said, we must realize that the death of God is an historical event, that God has died in our cosmos, in our history. And the dead God is the God of the historic Christian church beyond the church of and beyond church of Christendom at large. So here are two preachers telling their people who listen to them, God died in our time. That's really interesting, isn't it? How can God die? The only way that could happen is if we made Him up in the first place, which is where folks have ended up. So I'm telling you, class, if you'd been with me in my biology and chemistry classes at Florida State University and at Harvard in the 60s, you would have heard things like this. You folks who in this class are believers in God better get over it, because the time is coming very quickly that you will be an embarrassment to yourself and everybody else. Because we are learning more and more about what used to be attributed to God. And the more we learn, the less we need God. So you better get real, class. That's what I heard numerous times. I like this book better. It just came out recently. Is Atheism Dead? It's a book by Eric Matexas. I don't know how much you follow him. He's not a scientist, but he's a good writer. And he's done his research very well. And here's what he says. Since the Time article in 1966, roughly 5 things have arisen to challenge, and I will argue to overturn, the secular consensus that formed in the wake of that article. I like the way he says that, because it is the case. There was a secular consensus. You understand that? People turning away from God and hoping that things would be explained by natural causes. He says 5 things have happened since then that have turned that upside down. And I agree with him. Here's the 5 he lists. Science is now teaching us there's been a beginning. I'm not choosing to talk about that one tonight, partly because it's a little heavier and there's a way lot more math. And I know everybody loves math, but I'm getting over that one. But there is a lot of evidence from science that this universe and this world had a beginning. You know, I hope, that people used to say, no, this world is eternal. Matter is eternal. You don't need to explain how it got here because it's always been here. You cannot say that anymore, class. The evidence from science points to a beginning. Secondly, universe and this earth and life itself is fine-tuned. Again, that's a wonderful lesson. It's not what I'm choosing to talk about tonight, except in one piece, and that is stupefying complexity. Everywhere you look, it's overwhelming how complex things are, from the most massive things to the smallest things that you can possibly observe. And then he says, we've also learned archaeological discoveries that support the Bible. And then he said, the other thing we've learned is what atheism is and produces, and you don't want that. This book is worth the price of it by reading what he says about atheism in the 20th century. It is the 20th century class that is the century of atheistic governments. And they destroyed more people and undermined more things. They did more horrible things than is ever done in the history of mankind. You don't want it. And we have foolish people in our country today spouting communism. They need to go live in a communist country for a while and find out what it's really like. But that's not the lesson tonight either. I want to talk about stupefying complexity. So here we go, class. I'm going to start with a passage of Scripture because we're doing this in a church building. If I was doing this lecture in a chemistry lab on a college campus, I would not use the Bible at all. But I think it's appropriate in this setting to use a Bible passage to show you that God Himself has said in His book that this approach to studying the natural world is appropriate. So I ask you to take your Bible, if you have it, and turn to the theme passage for tonight and next Wednesday night. It's in Romans chapter 1 and verse 20. And I doubt that I'm talking to anybody in this class tonight that would disagree with this, so I'm not going to spend a lot of time with it. But here's what the writer, the Apostle Paul, by inspiration, says to us. Verse 20, "For since the creation of the world, His, that is God's, invisible attributes are clearly seen, being understood by the things that are made, even His eternal power and Godhead, so that they are without excuse." What does that passage teach? It teaches you can know there is a God by the indirect evidence of things that are made. You look at things that are made, and what's the first thing you conclude? Somebody, say it, somebody made it. Somebody designed it. God said that. And there's no excuse for missing it. That's what He said. So what I'm doing tonight is I'm making an argument from design. And that will be my argument all the way through this series. There's design everywhere you look. Somebody made this. So don't forget that. And it's biblically supported, Romans 1 and numerous other passages. All right. That leads me then to the evidence of chemistry of living things. So class, I've already welcomed you once. I'll welcome you again. Welcome to the first class of Biochemistry 101. We're so glad to have you in class. I have a number of things that I do regularly. One is I give pop quizzes a lot. So tomorrow morning, I'm kidding, but if you were in my class, that's what would happen. Because if you don't pay attention, and you don't keep up on a regular basis, you're going to get lost. I don't want anybody lost. So let's talk about life as we know it. So I thought I would turn then to a very famous biochemist named Francis Crick. Does anybody in this audience know who that is? Yes, he is the Crick of Watson and Crick. Those two gentlemen were given the credit for discovering the structure of DNA in 1953. So it's one of the early discoveries in this time period I'm telling you about. Francis Crick is world famous. I don't think he's still alive, but he was at this time. He wrote this book in the 1980s. And it's called Life Itself, Its Origin and Nature. So we're going to let him talk to us a little bit. I'm going to turn, first of all, to page 72 and read you a couple of paragraphs here. Life as we know it on Earth appears as a synthesis of two macromolecular systems. And I just lost you, didn't I? Let me simplify that for you. He says, every living thing that we know anything about has two types of giant molecules. Every single living thing. The proteins, because of their versatility and chemical reactivity, do all the work, but are unable to reproduce themselves in any simple way. So the first class of molecules is proteins, and I want you to say that with me. Please say, what is the first class of molecules? Protein. That's pretty good, class. I'm going to have you do it one more time. Get a little bit enthusiastic, will you? The first class of giant molecules in every living thing is? Protein. Thank you. Now that's better. And I will tell you in the next few minutes, the answer to almost every question I'm going to ask you is proteins. So you don't need to stutter around. The problem with proteins is they're great for doing the work, but they don't reproduce themselves. The nucleic acids, let's go through this now. Structural materials are proteins, and they are assembled from amino acids. These evolve the shape and mobility of living things. Secondly, there are tools and machinery. These are called enzymes. They are special forms of, say it, proteins. And they make up the metabolism, which is the growth and maintenance. So the structure, the stability, the growth and the maintenance, the mobility, those are all proteins. And class, there are thousands and thousands of them. They're extremely important, but they can't reproduce themselves. So the second great class is called the blueprints, the genes and the nucleic acids. The nucleic acids seem rather tailor-made for reproduction, but can achieve rather little else compared with the more elaborate and better equipped proteins. RNA and DNA, he says, are the dumb blondes of the biomolecular world. I'm sorry, I didn't say that, but he did. So you can take that as you wish. The problem of the origin of life, listen to me closely, would be a great deal easier to approach if there were only one family of macromolecules that could do both jobs. Reproduction and catalysis and other kinds of work. But life as we know it always employs two. If you don't remember anything else tonight from this first biochemistry lecture, you remember that. Every living thing has proteins and nucleic acids. You don't have life without it, and there is no form of life anybody knows one thing about that does not have them. I'll add one thing to that right now. That's the second thing I want you to remember if you don't remember anything else. They depend on each other. Totally. Can't have one without the other. Not to have life. All right, so that's our basic introduction. That's what life's about. Now, I do want to do one more thing here because I might forget it later. On page 88, he says this: an honest man armed with all the knowledge available to us now could only state that in some sense the origin of life appears at the moment to be almost a miracle. So many are the conditions which would have had to have been satisfied to get it going. And I say amen, except for the word almost. But folks, this was 1981. He can be partially forgiven. Not in 2026. We know way more about life itself now than he knew then. And I want to get over some of that to you this evening. So what does he do in the rest of his book? He says at the end of this chapter, if it was highly likely, there's no problem. But if it turns out it was rather unlikely that life started all by itself, then we are compelled to consider whether it might have arisen in other places in the universe where possibly for one reason or another conditions were more favorable. So you know what he does for the rest of this book? He has chapters on directed panspermia. Does that help you any? What he's saying is somebody sent the first life forms here on a spaceship. This is a Nobel laureate chemist, folks. And he spends 4 chapters talking about directed panspermia. Is there one scintilla of evidence that some guys sent this on a spaceship, the first life forms of Earth? There is 0 evidence for that. But they will take anything before God. That's the case. So I'm ashamed of Dr. Crick for even spending the time on this. This is supposed to be a prize-winning book, and half of it's pure conjecture. Garbage, I could call it. You notice it says proteins are assembled from amino acids, class. That's why in this first class, we've got to talk about amino acids. So there they are. You see before you, class, the 20 common amino acids occurring in proteins in all living things. May I say it again? I want it to sink in. If you take a protein out of a bacteria, like E. coli, you've all heard of that, you extract a bacteria protein, it'll be made of these. If you take one out of my wife, she's made of the same thing. I'm sorry, Marilyn, no offense. But it is the case that every living thing has proteins made out of these. Does that kind of strike you? You know what an evolutionist says about that? He says, why is it that we all have a common chemistry? Because we all came from the same tree of life. If you trace your ancestry back far enough, you go all the way down to the root of the tree, and it's one-celled organisms who evolved way back billions of years ago and then evolved into us. So we're all kin to each other. That's why we have the same chemistry. Folks, that is not a stupid answer. That's a possible explanation for our common chemistry, isn't it? It's possible it happened that way. What does a creationist say about that? Here's what I say. There's a better answer, that if there was a creator, would he need to start all over again every time he created something living? Why not use a common pattern for things that are going to interact and interplay with one another, maybe even feed on one another? Do you eat animal flesh and plant flesh? I think you do. So it would be good if your chemistry was coincident, wouldn't it? So those are both explanations for that. You got to look deeper than that to find a better answer. Is there evidence that God did this? That's where we're headed. But the fact is, class, these 20 common amino acids are in every protein in every living thing. Period. So don't you think you ought to learn them? So tomorrow morning, the first thing we'll do when they come in is I'll ask you to name these 20. So I'm going to read some of them to you. Glycine, alanine, valine, leucine, isoleucine, glutamic acid, glutamine, tyrosine, tryptophan, and histidine. They're not that difficult. Just learn the 20 names. And then learn their abbreviations. Can you see each one of them has a 3-letter word after it? Glycine is G-L-Y. Well, that makes sense. It's the first 3 letters. Leucine is L-E-U. Isoleucine is I-L-E-U. Isoleucine, and so on. You see that? So your first job is to memorize the 20 amino acids. And you say, why? Class, they're the foundation for every protein in every living thing. That's all. They're just the foundation for this entire class. The next thing you should do then, which we'll do the next day, is we'll try to explain to you why they're called amino acids. Every one of these, can you see the structures underneath? Every one of them has an NH3 in it. You see that right there? That's called an amine group because it has nitrogen and hydrogen in it, amine. And if you look at all of them, they all have an NH3 group. Can you see that? Every one of them. So they're called amino. So why are they called acids? Well, every one of them has a COO group. Can you see that? That's carbon bonded to 2 different oxygens. And it's in a certain configuration that makes it an organic acid because it gives off a hydrogen ion, which is what makes something acidic. So every one of them has an amine and an organic acid attached, so it's an amino acid. But beyond that class, every one of them is different, which means they have different characteristics. And that's critically important because that gives you proteins with a massive amount of variety. Massive. You can do any combination of 20 different things, taken however many at a time you want to take. Folks, some proteins have thousands of these in a row. You string a line of amino acids out as long as you want. A string of amino acids class is a weak. Let's try it again. A string of amino acids is a protein. Exactly. Every protein is a string of amino acids in a specific order. Critically important. Not just any old string works. In fact, most of them don't work. But the ones that do are amazing. Every protein is a combination of those 20. It's very much like in the English language, we have 26 letters. Every word in English is a combination of those 26 letters, isn't it? It's the same idea. String together amino acids, you get a protein. String letters of alphabet together, you get a word. It's the same idea. Are we good so far, class? Thank you for doing something with your head. And I'm watching you, by the way. I've been teaching a long time, and I know when you're getting ready to go to sleep. We have to leave proteins for just a minute and turn to the other great class of molecules, the DNA and the RNA. Here's a picture of the DNA strand. Can you see there's a strand like this, and then there's another one wrapped around it? And then you can see there's cross pieces. This one's colored up nicely, so you can remember. How many colors do you see there in the cross pieces? There's green and blue, right? And red and yellow. Now, do you notice that every time there's a red, it matches with the blue? And every time there's a green, no. Every time there's a green, it matches with the blue, and every time there's a blue, it matches with the green. The yellow and red always match up. So there's exactly 4 cross pieces. Let me put it up here. It's a double helix with crossbars, and thus it has the capacity to reproduce itself. That's the miracle, class. It can reproduce itself and a lot of other things, as you'll learn. And it contains a language we've learned since the 1960s, class. We've learned the language. It's called the genetic code. And it's founded on these 4 letters: adenine, thymine, guanine, and cytosine, which are the 4 cross pieces in DNA. So, your quiz day after tomorrow is to name these 4 and to tell me what's inside every DNA and RNA. There's a language that we know how to read, and we know what it does. It's amazing. And there it is. I have to throw in a little math. If you have 3 letters to use, no, you have 4 letters to use. And you can use them only to make 3-letter words. And you can repeat any of the 4 letters in these 3-letter words. So, for example, you could have a word that's A. That's pronounced ah. But that's a word in the genetic code. So how many words can you make that are 3 letters long that each one of those places can use any of the 4 letters? That's a combination problem. 4 things taken 3 at a time with repeats. The answer is 64. You can tell them how you got that? You just forget it. Here's how you get it. The first place can take how many different choices? 4. The second, how many? 4. And the third? 4. So it's 4 times 4 times 4. 4 times 4 classes 16, and 4 times 16 is 64. So up here on this chart, there are exactly 64 3-letter words. Let me show you something about that, and I'm going to have to be really quick tonight on this. You see those 3 right there that say term? TAA, TAG, and TGA, it means term. That means terminator. What that means is that code means stop reading or stop doing whatever you're doing. If I terminate you, sir, you're dead, right? It's over. Those codes mean terminate. So that takes away 3 of them. That leaves you with 61 more, doesn't it? Those 61 are divided up among, well, you tell me. What is this PHE here? PHE. You were supposed to memorize the 20 amino acids class. That was yesterday. Yeah, look at your notes real quick. PHE stands for phenylalanine. That's one of the 20 amino acids. So I'm telling you, this code right here, TTT, which you rather pronounce this is not a spoken language. But TTT means phenylalanine. So does TTC, and let's see, I guess that's the only 2 on that one. How about TTA? What do you know? Can you recognize that one? LEU? Leucine. Yeah. And leucine has 1, 2, 3, 4, 5, 6 codes because there's only 20 amino acids and there's 61 words you can use. Got it? So there's repeats. I call that a backup system. Right? So up here, class, you have all 20 amino acids represented, plus 3 codes for terminating. And the one I didn't tell you about, let me go back here, is this one right here. ATG means methionine, but it also means start reading. So everybody's eyes up here. If you got a string of amino acids, you have a protein. That was weak, class. If you have a string of amino acids, you have a protein. It's got to start with an amino acid and stop with an amino acid, does it not? Every amino acid starts with methionine. They stop with one of the terminators. And in the meantime, you have 3-letter words. 3-letter word, 3-letter word, 3-letter word, 3-letter word, 3-letter word, all hooked together. And when you get to terminator, you stop. And the string between methionine and the last one you terminate with is an protein. Thank you. That's right. And that's how the code works. So in that second pop quiz, I'm going to ask you to read. And I won't ask you to memorize this. You can use a cheat sheet. So if I gave you the word ATT, tell me what that is. Can you see it well enough? ATT. I know it's kind of small. I'll point it out to you right there. What does that stand for? ILE. That's isoleucine. Right. So your job's to learn how to read, class. And it's very important because the sequence of amino acids in that protein absolutely determines what that protein can do and not do. And the chemistry of each of those amino acids is vitally important to what they can do together and cannot do. And we have lots to talk about. So all 20 amino acids are here, and I told you a stop and a start. But there's so much more to this, class. That's just the starting. But I will tell you what I believe. If this were a court of law and you were my jury, I would rest my case that God did this. Because there is no evidence anywhere that anybody knows that anything that produced a language came about by itself without an intelligent designer. Are you listening? And yet in every living thing, there is a language. And the language is doing things at an enormous rate of speed, and it makes all the difference between life and death. And you tell me, ladies and gentlemen of the jury, that something over millions of years just developed into a language that produces living things? You sincerely believe that? If you do, you need your head examined. That is sufficient in and of itself to say God designed this. This did not happen by natural causes. But I will tell you there are beaucoup multiplied thousands of scientists that would laugh at me and think I belong in the dark ages. No, folks, I'm dealing with modern, up-to-date information. Ages ago, they knew nothing about a language inside every protein and every DNA and RNA. We do. We have less excuse than the Dark Ages. And now, class, in our particular type of cells, you and I are a little more advanced beings. We have what are called eukaryote cells, that is, cells that contain within them a nucleus. Prokaryotes, like E. coli and other bacteria, do not have nuclei in their cells. They're just a blob that have stuff in them. Eukaryotes have nuclei. That's what I'm going to focus on because we care most about us, don't we? I mean, you may think something about roaches and fleas and worms and other things, but we're most interested in humans. So that's what I'm going to talk about. We are eukaryotes, class. That means all of our cells have a nucleus. You see the nucleus up here? And then it have a cytoplasm. So this is the outside of the cell. This is the nucleus of the cell. And most of the DNA in your cells is in the nucleus up here. That's the DNA up there. And a lot of the activity starts there. Then there's a nuclear membrane. You see it? And then outside is the cytoplasm that is in the cell itself. And then there's a cell wall. So there's two basic areas, inside the nucleus and outside the nucleus. And so here's what you do in those domains. I want to talk with you, class, for the next few minutes about how you build one protein. How does a protein get built in your cells? By the way, first, did you know that proteins are built? They're built. Your body builds them. It builds them from starting with basic materials. And then from those basic materials, it makes proteins. And it's an amazingly complex thing that goes on that we've only learned about really in the last 75 years. So what we've got in this process is transcription, migration, and translation, all of which are required for protein building. Transcription, what does the word generally mean? If you transcribe something, somebody tell me, what does that mean? You rewrite it, don't you? You copy it over. In other words, there's something that's already there and then you make a copy of it. Well, what's the truth, class, is the DNA has all the information in it. It stores information. It is the most massive storehouse in the universe. There's nothing to match it. And it's all crammed into almost no space. But the information for every living thing and every part in it is in the DNA. So the information's up here, but the action's out here. So if you're going to build a protein, you got to take the information off the DNA first. That's transcription. And then the things that you've copied, they're called RNA. Don't tell me that's the end of this class. Are you kidding me? Guess what we're going to do next Wednesday night? We're going to pick up where we left off. Well, you got to hear this. All right, the next thing it has to do is migrate. You've made three kinds of RNA: messenger RNA, ribosomal RNA, and transfer RNA. You have to make those first. That's transcription. Then they have to migrate outside that cell wall out into the cytoplasm. The messenger RNA is picked up by two ducks hugging each other. Wrong. That's just a picture. These are called ribosomes. And the information that's been copied up here that has migrated is now read through the ribosomes as it translates the information from up here into proteins. That's what happens. Now that is a miserable, incomplete description. There are thousands of things that I skipped over. And I'm not exaggerating one little bit. But that's the basic picture. So let me just do this much. I have 3 minutes. In order to make one protein class, you have to copy the information, make the RNAs, migrate, read them, and then through the process of this down here of translation, you make the protein. Every piece of that requires proteins. You didn't get it. To make one protein requires a bunch of steps. And every one of those steps requires proteins. So the real question is, how'd you get the first one? Or the third one? How did you get the first protein if it requires proteins to make them? And it does. Lots of them. My goal this evening was to finish with the grand number that I've been calculating over the last week. Folks, I've spent a lot of time the last week trying to figure out how many proteins it takes to make one protein. It's a massive job. And I'm not telling you that tonight because it's no fair to make me stop as soon as you are. If this weren't a VBS, I'd make you stay. But I can't do it. But I'm telling you, class, let's just go through this briefly. You see that DNA has to unzip up here to get the information off? Guess what it takes, class, to unzip DNA? Say it. Protein. Excellent. In order to zip it back, what do you think it takes? Protein. Yeah, your zipper ever gets stuck? Yeah. So can DNA. You have to have a specialized protein to zip it back up. There are a bunch of other proteins needed. Here you've got the messenger RNA. Do you see those white spots in it? Those are called introns. They have to be snipped out and it has to be re-edited. Guess what that takes? Proteins. They're called editosomes and spliceosomes. They're extremely complex, massive machines made out of proteins and other stuff. What about migration? You say, surely it doesn't take proteins. Yes, it does. Every time you want to make a protein, it's got to have a bunch of stuff going on when it migrates. For example, when it comes up to that hole, do you think any respectable nuclear membrane is going to let just anything go through that hole? No. What do you think guards the hole? Protein. Exactly. There's specialized proteins. There are over 30 different proteins that guard that hole. And when that messenger RNA comes up to it, it's got a protein attached to it with a special message. They say, okay, come on in. And it goes through the membrane, comes out the other side, and then there's another bunch of proteins that close it back down because they don't want it coming back. Bunch of proteins involved in migration. Haven't touched the hem of the garment. Now it's outside the cell wall, the nuclear wall, and it comes down here to the ribosome. It took some proteins to get it from here to here because there's challenges. Haven't talked about that. More proteins. When it gets down here, then you got to start bringing in the transfer RNAs with each of the amino acids. They come in here. Each transfer RNA, there are exactly 20 of them, and they have exactly one specific protein for each one. So how many is that? 20 proteins more that are required to bring in the appropriate amino acids inside this ribosome, inside there to hook them up. Guess what it takes to help them hook up? Proteins! And when you get through making this protein down here and it's exported, class, listen to me closely. That's what I spent most of my time on yesterday and today. There are post-translation activities that take place with every protein. The first one is you got to snip off that methionine most of the time because most proteins don't want methionine at the beginning of it. So it's snipped off. That's a process. Guess what it takes to make that happen? A protein. And then the thing has to fold up on itself. Don't watch the kids, watch me. It has to fold up on itself in a specific way. What do you think it takes to make that happen? Proteins. And then after that gets done, there's another process that goes to the endoplasmic reticulum and then to the Golgi bodies. And in each of those places there are more to make it do more stuff, either added or subtracted or to fold it better. And then to identify where's it supposed to go. What do you think that takes? Protein. Yes, ma'am. And sir?
So eat protein.
You better eat your protein. And class, That kind of stuff, building proteins, is going on in every cell of your 30 trillion every second. And somebody says, isn't it interesting how for millions of years, that incomparably complex, stupefying process that is founded firmly on a language came about by Darwinian evolution over millions of years with small changes over millions of years. It is the biggest fairy tale that's ever been told. And intelligent people at Harvard University are teaching it all the time. And they know very well what I'm talking about. But so did Francis Crick when he made up the story that somebody sent the first life forms here on a spaceship. I have so much more to talk to you about. I'm totally frustrated. But we'll pick up this lesson next week and try to cram in a little of the next one also. And then you're going to invite me back, I hope, for lessons 4 and 5 and 6. All right, it's time to stop. Thank you so much. Appreciate your kind attention. And may God be praised in all of this.